Good morning to all of you. I am KVSS Ramakrishna, working as Assistant Professor in the Department of CSE, Vignyas Nirula. We are going to discuss about a subject that is called as Formal Languages and Automata Theory. It is Formal Languages and Automata Theory. This is the subject that what we are going to discuss. Now, under this subject, first of all, let me explain you what is the syllabus of the particular subject. So this is the unit 1 syllabus. As you are seeing, this is the unit 1 syllabus. Now, the concept that what we are going to discuss is why we have to study the automata theory. There are various applications where we can use the concept of formal languages and automata theory. Especially in compiler design, in order to design a compiler, we might be using a concept called as this formal languages and automata theory. So there are various applications of this formal languages and automata theory. We are going to discuss them in detail as the syllabus progresses. Now, the second thing that what we are going to discuss is the central concepts of the automata theory is the second concept that what we are going to discuss. Under this central concepts of automata theory, mainly we are going to discuss about 4 concepts. The first concept is a symbol, second concept is an alphabet, and third concept is a string, and the fourth concept is a language. Later on, we are going to in detail explain all the things. Then we are going to have about automation. What do you mean by automation? That is followed by finite automation. After that, we are going to see about transition systems, and we are going to see about acceptance of a string by a finite automation. Then we are going to see about most important concept and most tricky concept, and that is called as deterministic finite automata. We simply say that, in shortcut, we say that it is DFA. This is what we are going to study. Then after that, we are going to have certain designs of DFS. We are going to have examples of DFS. Then we are going to discuss about NFA. NFA stands for non-deterministic finite automata. Later on, we are going to have the design of NFS, like the design of DFS. After that, we are going to have the equivalence of DFA and NFA. Then after that, we are going to have the conversion of NFA into DFA. After that, we are going to have finite automata with epsilon transition. Mind that this is not E, this is actually epsilon. This is the symbol. Okay. So, this is the step-by-step process. Once you understand DFA, you can understand NFA. Once you understand NFA, then we can have the equivalence between NFA to DFA. Means what? Each mission, that is NFA mission, we can convert it into DFA. After that, we are going to have NFA with epsilon transitions. We can convert it into equivalent NFA, and then we can convert it into equivalent NFA. Without epsilon, then with epsilon, without epsilon, then DFA. That is the procedure. Means what? NFA with epsilon to NFA, without epsilon to DFA. Now, minimization of the finite automata, we are going to discuss it. Then after that, we are going to see about milli mission and more missions. After that, we are going to have the applications and limitations of finite automata. This is about the syllabus, unit 1 syllabus. We are going to cover them one by one. Now, I am starting with the concept called as central concepts of automata theory. Now, the first concept that what we are going to discuss is the symbol. Let me explain you the symbol. Now, this is the symbol that what we have written. Now, what do you mean by symbol means a symbol can be defined as the smallest individual unit that cannot be further divisible. Understand this. I said that a symbol can be defined as the smallest individual unit that cannot be further divisible. You can't further divide the symbol. For example of a symbol, let me say that it is a dollar symbol. This dollar symbol is a single character. You can't divide it further. That is the meaning of it. Or I can say that it is a hash symbol that you can't further divide it. I can say that small a is a lowercase English alphabet. That is a symbol that cannot be further divisible. So, I can say that capital A is the uppercase English alphabet letter. So, what do you mean by symbol? A symbol can be defined as the smallest individual unit that cannot be further divisible, and all these are examples of symbols. That is the first central concept of automata theory. Now we are going to discuss about, this is the first one. Now we are going to discuss about the second one. So the second one, what we are going to discuss is, we are going to discuss about the second central concept called as alphabet. See, what do you mean by alphabet means, we can define the alphabet as a finite, non-empty set of or collection of symbols is called as an alphabet. Alphabet in formal language and automata theory, we are going to define them as, it can be defined as a finite, non-empty set of symbols. Finite and as well as non-empty set of symbols, we can treat it as an alphabet. So an alphabet consisting of a set of symbols which are finite in number. I can't have a set which is not having any element. If I don't have any element in a set, we say that it is an empty set. But the alphabet is saying that alphabet can be defined as a finite, non-empty set of symbols. Number of symbols should be finite. At the same time, it should not be empty. What are the various examples that what we can give for an alphabet? In general, normally we are going to denote the alphabet in formal language and automata theory by the letter sigma. So whenever I use the letter sigma, this is nothing but an alphabet. It is nothing but an alphabet. So an alphabet in formal language and automata theory is always represented or denoted by the letter sigma. So we have this sigma as a letter to denote the finite, non-empty set of symbols, which is nothing but an alphabet. Examples for alphabet means we can have several examples for alphabet. We can give several examples for alphabet. For example, we can start with binary alphabet. As the name indicates that binary means 2. So we are going to have 2 symbols in the binary alphabet. You know it, that is one is 0 and the second one is 1. So if it is a binary alphabet, then the symbols will be of finite, and finite means what? How many symbols are there? 2. 2 means finite, and a non-empty set of symbols. This set is not empty. Why? Because it consisting of 2 elements. So this is an example for binary alphabet. Similarly, I can give the example for a ternary alphabet. Ternary, ternary alphabet. In ternary alphabet, as the name indicates that ternary means 3, we are going to have 3 symbols. One is 0, second one is 1, third one is 2. This is what is called as a ternary alphabet. Similarly, we can have octal alphabet, hexadecimal alphabet, lowercase English alphabet, uppercase English alphabet, like that. For example, lowercase English alphabet means what? Small a, small b, and so on till z. Means 26 letters we are going to have in total, which is finite in number, and as well as it is not empty. So this is the second concept called as alphabet. So alphabet can be defined as a finite, non-empty set of symbols. Okay, binary alphabet, octal alphabet, ternary alphabet, decimal alphabet, lowercase English alphabet, uppercase English alphabet, ASCII characters, set of ASCII characters. We can also treat it as an alphabet, which is represented or denoted by the letter sigma. So this is about the second central concept of automata theory. First one is symbols, second one is alphabet. Now we are going to see about the next one. The third concept in finite automata theory, that is central concepts of finite automata theory, is the string. As you know that a string can be defined as a sequence of symbols or collection of symbols. Sequence of symbols, right? That we can treat it as a string, or we can say that it is a word. So in formal language and automata theory, we can define the string as a sequence of symbols or sequence of characters, and we are going to get it from the alphabet sigma. Whatever the alphabet sigma is having, from that only we are going to form the words or strings. Now suppose I use the word suppose. If you imagine, I use the word suppose. See, this is the word that I am using. This is suppose. So I form the word suppose. S is coming from English alphabet. U, P, P, O, S, E. All of them are actually coming from English alphabet only. So the words are actually coming up from the alphabet. Alphabet is actually coming from set of symbols which are finite. So in that way there is a connection between them. So we can always represent the string or word in formal language and automata theory with a letter called as W. With a letter called as W. And whenever I use the word, I use the notation mod W, it is actually going to give the length of the string. For example, let me use the word called as hello. Let me use the word called as hello. W is equal to hello. So it is a word that is actually coming from alphabet, and alphabet is nothing but a finite non-empty set of symbols. So from symbols, you are going to combine a finite non-empty set of symbols. If you combine them, it will become an alphabet. From alphabet, we are getting words or strings. Suppose the W is equal to hello is a word. What is the length of the string? You just count the number of characters in the string W. That is 1, 2, 3, this is 1, this is 2, 3, 4, 5. So length of the string is mod W, that is represented as 5. That we are going to get a value of 5. Means what? We are going to see 5 characters or symbols in the string hello. So that is what is called as mod W, which is always going to give you the length of the string. This is about the third central concept of automata theory. First one is symbols, second one is alphabets, third one is strings or words. Always we are going to represent the alphabet in formal language and automata theory with which letter? Yes, correct. It is sigma. Always we are going to represent a word or a string in formal language and automata theory with which letter? Yes, correct. It is W. So whenever I say that I want to calculate the length of the string, what is the notation that is what we use normally in flat? That is mod W. Yes. So this is about the third one. Now we are going to see about the fourth one. Before we proceed the fourth one, that is languages, we are going to have some more concepts on alphabet. We say that the power of an alphabet, as you are seeing, that is the power of an alphabet. This is the powers of an alphabet. See, alphabet always we are going to represent it with the letter sigma. Now let me explain you what is the power of an alphabet. If I say that sigma power 0, what do you mean by this? See, we can say that it is the set of all strings or words whose length is of 0. That is what is called as a power of an alphabet. Means sigma power 0 means that it is going to contain set of all strings whose length is 0. The set of all strings whose length is 0, we call it as with a special symbol called as epsilon. Whenever I use the word epsilon, it is actually represented by this letter, and it is going to represent you an empty string. An empty string. What do you mean by that? A string whose length is 0, mod epsilon is equal to 0, whose length is 0 is called as an empty string. That's what is called as a sigma power 0. Now what do you mean by sigma power 1? It is going to have set of all strings whose length is 1. What do you mean by sigma power 2? It is going to contain set of all strings whose length is 2. Sigma power k means what? It is going to contain set of all strings whose length is k. That is what is called as a power of an alphabet. Here you are going to see about two important things here. What is that one? Sigma star. We use the word star as to represent clean closure. We are going to use the word plus to represent the positive closure. So clean closure means you are going to have a set of all strings whose length even starting from 0. So you can always have epsilon in sigma star where you don't have epsilon in sigma plus. What do you mean by sigma plus? Means it is a positive closure where you are going to start the set of all strings whose length is actually starting from 1 but not with 0. So sigma power 0 here means epsilon will be included and all the remaining thing here and here are same. So what is the relationship between sigma star and sigma plus? I can say that sigma star, since sigma star is having epsilon, whereas sigma plus is not having epsilon. So I can say that that is nothing but sigma plus, or we can say that plus or union, we can say that epsilon. Means sigma star is equal to sigma plus union epsilon. So this is the relationship between the clean closure and pass-through closure. So this is about the power of an alphabet. We have covered what do you mean by symbol, we have covered what do you mean by a string, we have covered what do you mean by an alphabet, and now we have covered what do you mean by power of an alphabet. Symbol, then after that we are having that alphabet, after that we are having the string, after that we are having the power of an alphabet. That is the sequence. Now we are going to see about the next one, languages. This is the fourth and last central concepts theory, the concepts of the automata theory, central concepts of automata theory. A language, actually whatever the language that I am speaking right now is an English language. So how I am going to form the language with the help of strings, whatever the words that I am using right now, right is a word, now is a word, that is actually coming from where? It is coming from the strings. So collection of strings is nothing but a language. Collection of strings is nothing but a language, and especially we can say that collection of appropriate strings can be defined as a language. So we are going to have an important relationship between a language and the sigma star, and we can always say that the language L, we can always say that the language L, yeah, this is the word I am going to use. This is the language, capital L is always a subset of sigma star. Why? Because sigma star is going to have set of all strings of any length, of any possible length. I can have set of all strings whose length is 0, means epsilon, set of all strings whose length is 1, set of all strings whose length is 2, and so on up to infinity I can go. So I can say that is nothing but sigma power 0 union sigma power 1 union sigma power 2 union and so on, sigma power I can go up to infinity. So I can say that language is subset of sigma power 0, sigma power 1, sigma power 2 and so on. So this is the symbols, alphabet, strings and the languages L. Here we can see that this is an epsilon, this is actually an epsilon 0 1 0 0 1 1 0 0 0 1 1 etc. Now let me explain this. Yeah, if you are saying L is said to be a language, L is always represented, it is going to represent language. So in fact we are going to follow certain standard convention. Symbols, alphabet is represented by the letter sigma, whereas W is always going to represent a string or a word, and we are going to have the sigma star is going to represent is a clean closure, and sigma plus is a pass-through closure, star is a clean closure, plus is a pass-through closure, and W is a string, and mod W is a length of string, capital L is a language, and sigma represents an alphabet. These are all the standard notation that what we are going to see. L is said to be a language over the alphabet sigma only, if and only if L is subset of sigma star. That's what I have explained you. For example, let me see the language. Let L be the language of all strings consisting of n zeros followed by n ones. N zeros followed by n ones. If n is going to start with 0 and onwards. So zero number of zeros. If n is equal to 0, what do you mean by that? 0 number of zeros are followed by 0 number of ones. So nothing is followed by nothing. Means epsilon. It's an empty string. 1 number of 0 is followed by 1 number of 1. 2 number of zeros followed by 2 number of ones. That is the exact meaning of that one. So what is the second language that what we are going to see is, let L be the language consisting of set of all strings with equal number of zeros and ones. Equal number of zeros and ones means what? See, if I say that epsilon is going to have equal number of zeros and ones, obviously yes, of course, yes. Why? Epsilon contains 0 number of zeros and 0 number of ones, means what? It won't contain anything. So we can say that epsilon consisting of equal number of zeros and equal number of ones. I can use 0 1, I can use 1 0, I can use 0 1 0 1, I can use 1 0 1 0, I can use 1 1 0 0, I can use 0 0 1 1. I can have several combinations. In all those strings, see, if I say that 0 1, it is valid, epsilon it's valid, 1 0 1 0 it's valid, 1 0 0 1 it's valid, and 0 0 1 0 1 it's valid. See, you count the number of ones here 2, here count the number of zeros here 2. So number of zeros are equal to number of ones. In that way you can understand. Now this is an important question. Is L is equal to 5? Let L is equal to epsilon. This is epsilon. If L is equal to epsilon, is L is equal to 5? No. See, L is equal to epsilon means the language consisting of an empty string. An empty string. Means what? Phi means an empty string means the language does not contain anything. But whereas epsilon is having a special meaning, understand this. There is a huge difference between epsilon and phi. Phi denotes it's an null set, means the set that does not have any elements. Whereas epsilon is an element whose length is 0. It's a string whose length is 0, means it's an empty string. Epsilon is an empty string. Phi, what do you mean by that? Phi is an empty set. The set that does not contain anything, but the set that consisting of element whose length is 0 is epsilon. Both of them are not equal. Epsilon is not equal to phi. That you need to understand. Is L is equal to phi means? No. That is the answer. Now we are going to see about the finite automata theory. We are going to see about certain simple applications of this finite automata theory. We are going to have the simple applications. Now, as you are seeing on the board, some applications of the finite automata is software. We can use it as a software for what? For designing and as well as checking the digital circuits. In the construction of designing and as well as checking the digital circuits, we are going to make use of the concepts that what we are going to study from formal language in automata theory. Next, you are going to have the lexical analyzer of a typical compiler. You know that what you mean by a compiler, what is the purpose of a compiler. In order to construct a compiler, we are going to make use of several concepts from formal language in automata theory. So, in compiler is going to have various phases. In one of the phase, we are going to have the lexical analyzer of one of the phase of a compiler. In order to construct it, we are going to make use of concepts of the formal language in automata theory. We are going to make use of this formal language in automata theory to construct a software for scanning large bodies of text, for pattern finding, for regular expressions. We are going to make use of these concepts. And the next application that what we are going to have is, we can construct a software for verifying systems of all types that have a finite number of states. So these are all some of the few applications of formal language in automata theory. So whatever the concept that what we are going to discuss under formal language in automata theory, these are the various applications. You can build a compiler, especially lexical analysis phase will be there of a compiler. We are going to make use of the concepts of flat only to construct that one, as well as digital circuits designs. We are going to make use of them. These are the some applications. Okay, these are some applications. Now we are going to see about the next concept, finite automata example, that is on-off switch. If you carefully observe the on-off switch, this is the on-off switch. Now this is the on-off switch I am talking about. So always the states, we are going to introduce a term called as a state. A state is always represented in formal language automata theory as a circle. Within the circle you are going to write something, and this is called as name of the state. Here Q0 is the name of the state. Similarly, a bulb will be having two states. One is on state, second one is off state. A switch is also going to have two states. One is on state, second one is off state. So this is a starting. At start, you are going to, this is a standard notation that always we are going to use in flat. These are the two states, off state and as well as on state, and this is an on-off switch. A switch is always going to have two states. One is on, second one is off. Initially, the switch will be in the off state. So this is the, at start we are going to have off state. Whenever you are going to press the switch, it will go into the on state. Yes or no? Yes. So press means push. Whenever you perform an activity push, you are going to make the state of the switch from off to on. You are going to transit it. So again, one more push if you make on the switch, then it will go to the off state. So there are two states. One is off and second one is on. And one transition we are going to apply, either to make the switch from off to on, we are going to make use of push, or we are going to make use of the same push to bring it back to the off state. So this is the transition. This is what is called as a transition diagram. We use a word called as a transition diagram. And this is an example for transition diagram only. This is the example for what? Transition diagram only. So this is about the state diagram or transition diagram. Simple on-off switch. Now we are going to see about modeling recognition of the word then. Suppose that you want to make a word that is then is acceptable. See, in flat we are always going to have a concept called as starting state, and as well as a concept called as final state, and a concept that is called as an intermediate state. Suppose that starting states we always represented with a letter Q0 normally, and if it is a starting state, I am going to write start on the just the arrow mark above. We are going to represent as start. That is Q0 state. Now suppose that I am going to use the T here T. I am going to go to the state Q1. What do you mean by this? Means if I apply T on Q0, I will be changing from the state Q0 to Q1. So what is the next letter in then? H. So if you apply H here, then I am going to go to a state, say that it is Q2. Till then Q2 remembers that I have seen T, I have seen H. 2 letters it has seen, TH. After that, if you apply E, I will go to another state Q3. Q3 is saying that I have seen THE. Then if I apply another letter N, now this is the letter that what I am looking for. Okay, then is the word. Now since the then word I got it, what I am going to do, I am going to halt it. Means what is, it is an acceptance state. Suppose that it is Q4. Q4 can be called as an final state. So if you observe the diagram, Q0 is the starting state, whereas Q1, Q2, Q3 are the intermediate states, whereas Q4 is the final state. Normally what happens in flat is we always going to represent states with certain special symbols. Means if you write a circle and within the circle if you put something, it is called as a state. Okay. Now in order to represent a final state, we are going to see about two main things. Final state we can represent it as with a double circle, or we can represent a final state as by a single circle, but within the circle you are going to write star. Then also it is final state or acceptance state. This is how the diagram can be explained. Now finite automata, formally we can say that a finite automata is a state diagram. Actually what we have seen, the on off switch is going to have the state diagram only, that is going to comprehensively capture all possible states, on state, off state, like that, and transitions. What are the transitions? Push and push. Two transitions are push in case of simple switch. Okay, and that a machine can take while responding to a stream or a sequence of input symbols. We can use, let me explain it. We can use this finite automata as a recognizer. That's what is called as a then word. Then is the word that what we have recognized as a regular languages. Now we are going to have two types of automata here. One is a deterministic finite automata, and the second one is non-deterministic finite automata. We are going to explain them in the next concept. Okay. So this is the, as the name indicates that it is the deterministic finite automata. It is a deterministic finite automata. This is deterministic finite automata. We always use a word called as a DFA. DFA stands for deterministic finite automata. Actually, deterministic finite automata is a mathematically we can represent as a 5-tuple notation. The first tuple we can say that it is capital Q. It is a finite non-empty set of states, and sigma is an alphabet. Delta is a transition function, and we are going to have another two couples, Q, sigma, and transition function delta, and we are going to have a starting state Q0. We are going to have a one or more finite set of final states represented by capital F. This is first tuple, second tuple, third tuple, fourth tuple, fifth tuple. In that way, we are always going to represent the DFA mission with 5 tuples. Mathematically, we can represent a DFA, deterministic finite automata, by using 5 tuples. Q, capital Q, finite non-empty set of states. Sigma is an alphabet, and delta is a transition function. Here in the DFA, we are going to have the transition function as delta maps Q cross sigma goes to Q. I will later explain why we call it as. What is the reason behind obtaining this transition function? Anyhow, it is a transition function. Delta maps Q cross sigma goes to Q. This is about the deterministic finite automata. Now, what does a DFA do? on reading an input string. See, on reading an input string, DFA may be accepting the string or may be rejecting the string. If the string is there in the language, the DFA machine can consume the string symbol by symbol. Once it is going to consume the entire string, if it remains in the final state, we say that the string is accepted by DFA, otherwise we say that the string is not accepted by DFA. So for that, what we are going to see, suppose that you want to recognize the word called as then. Okay, you want to recognize the word called as then. Let me explain this. Then. Now normally, the normal strategy that what we use, first of all, whenever you are going to design a DFA that is going to accept a string then, how many number of symbols are there here? T, H, E, N. How many symbols are there? 4. If there are n symbols, at least we may require n plus 1 states. That is the rule, thumb rule. Okay. If there are n symbols, how many symbols are there? 4. So we may at least require n plus 1, means what? 5 states. So Q0, starting from Q0, Q1, Q2, Q3, Q4. Q4 is the final state. So in order to answer it, what I am going to do, first I am going to, this is the starting state or initial state, and that is the final state. I am going to apply T here. After I see T, I will apply H. After I see H, I will apply E. After I see E, I apply N. So if this is the sequence that is followed, we say that the string is accepted by the DFA, otherwise it is not. Suppose that, assume that, so the third symbol, instead of E, I am going to have C. This string is actually rejected, okay? Then we won't make the automata to be in the final state once it consumes THCN, okay? So this is about the procedure. We are going to start at the starting state Q0. For every input symbol means T, H, E, N of the string W means then. What we are going to do, we are going to compute the next state from the current state, okay? So in that way, we are going to check whether the string W, this is the W, means then is accepted by DFA or not. We are going to check it out. Now we are going to see about the example. Build a DFA for the following language. L equal to W is a binary string that is going to contain 0, 1 as a substring. So in order to do this problem, we have to always take it in our mind that we are going to have a thumb rules or certain rules should be understand. You should understand before you start solving a problem of DFA. The first one what we see is, suppose that here the problem is W is a binary string. So let me explain it. W is a binary string. Okay. So W is a binary string. Binary string means alphabet is a binary alphabet that contains of two symbols 0, 1, and the string contains 0, 1 as a substring. 0, 1 as a substring. So how many symbols are there in the string 0, 1? For 0, 1 string, I need to construct a DFA. I need to construct a DFA for which is going to accept set of all strings in which 0, 1 is going to appear as a substring. What is the example? Suppose that what is the minimum substring that I can have? 0, 1. So what is the other substring that I can have? 1, 0, 1. Since 0, 1 is there in 1, 0, 1, we say that this is a valid word, okay, that exists in the language. This is also a valid word. Can I say that 1, 1, 0? No, this word is not in the language. So you have to construct a DFA in such a way that it is going to always accept set of all strings in which 0, 1 appears always as a substring. So such type of DFA machine that what we are going to construct. So how many symbols are there here? 2. So how many states we may require? At least 3 states. Let me start constructing the DFA. Here itself I am going to show you how I am going to construct a DFA machine. I am going to start with Q0. Since 2 symbols are there, I may require 3 states. 0, Q0 on 0 goes to Q1, and Q1 on 1 it goes to the final state. What is the minimum string that is acceptable here? 0, 1. That is the minimum string. Now is it a DFA machine? Means whenever I want to say that a finite automata is a DFA, it has to satisfy 2 rules. What are the 2 rules? See, whatever the symbols that what we are having in the alphabet, we have to consume all the symbols in the alphabet on all the states. How many states are there? 3 states are there, right? So I have applied 0 on Q0, but I have not applied 1 on Q0. But I need to apply 1 on Q0 as well as 0 on Q0, 1 on Q1 as well as 0 on Q1, 1 on Q2 and as well as 0 on Q2. That is the first thumb rule. Means what? All states should consume all input symbols is the first thumb rule in DFA, in construction of DFA. And the second thumb rule that what we are going to use is, whenever you apply a symbol, suppose that you are going to apply a symbol 0 on Q0, it will go to one and only one state. On the application of the symbol 0, it has to go to only one state. On the same symbol that is 0, you should not go to some other state. So in DFA, whenever you are going to apply a symbol on a state, you should always going to go to only a unique state. You should not go to any other state which is different from the previous one on the application of the same symbol. So Q0 on 0, you should go to Q1. So it should not go to any other state except Q1 on the application of the same symbol 0. Is it a DFA? No. Why? Why? Because you are having 2 paths. Since you are applying 0 on Q0, it is going to go to 2 states Q1, Q2, which is not correct. So these are the 2 thumb rules. The first thumb rule is saying that all the states should consume all the input symbol, and the second thumb rule is saying that on the application of an input symbol on a particular state, it should go to only one and only one state. Now I am going to consider this Q0 on 0 that is going to Q1, on 1 going to Q2. I am going to consider a DFA that I am going to have a set of all strings that contains 0, 1 as a substring. The minimum substring that what we can have is 0, 1. Is it a DFA? No. How I can make it as a DFA? I can make it as a DFA by applying all the symbols on all the states. I have applied 0 on Q0. Have I applied 1 on Q0? No. You need to apply it now. So can I apply it as a self loop of 1? Of course, yes. Why? See, suppose that if I apply 1 as a self loop on Q0, let me check it out. Q0 on 1, where it is going Q0 only. So 1, I am at Q0. And I apply 0 on Q0, I will go to Q1. And I apply 1 on Q1, I am going to go to Q2. See, this is the string, final string 101. Is this final string is going to contain 01 as a substring? Of course, yes. So I can apply 1 on Q0. There is no problem. There is not at all any problem. Okay. Is it a DFA? No. Why? Why? Because you have shown a path for 1 on Q1 but not shown a path for 0 on Q1. Now I need to apply 0 on Q1. Can I apply it as a self loop? Do you have any problem on that? I don't think so. Let me check it out. So Q0, I have applied 0 on Q0, I moved to Q1. I have applied 0 on Q1, I will remain in the same state Q1. And finally, I have applied 1 on Q1 and going to the final state Q2. This is the final string 001. Is it containing the 01 as a substring? Yes. So I don't have any problem by applying 0 on Q1. I think you are understanding. Now, what about the Q2? I have not applied 0 on Q2 and as well as 1 on Q2. Now I need to apply both 0 and 1 on Q0. Let me say that what happens if I apply 0 as a self loop on Q2? Do you have any problem? See, once you reach Q2, definitely you might have got that substring 01 already. See, whenever you are going to Q2, you always go to Q2 with the substring 01 itself, right? So once you reach the final state, already I got the substring as 01. It doesn't matter for me whatever the symbols that I apply. Why? Because already I got 01, then only I have reached it to Q2. I think you are getting it. So applying 0 and 1 on Q2 does not have any problem for me. So let me check it out. Q0 on 0. I have applied 0 on Q0, I am going to state Q1, and I have applied 1 on Q1, I am going to Q2. Suppose I have applied 2 times 0 and 2 times 1. See, what is the string 0, 1, 0, 0, 1, 1? This string is going to contain the substring as 0, 1? Yes, of course. So this is how we are going to construct a DFA. Okay. Now we are going to see about the next one. DFA for a string containing 0, 1. This is the diagram that what I have explained you. If you understand this, you can understand this. Okay. So this is starting state Q0, 0, 1. This is the minimum string that what we can have. Go to Q2, accept it. Okay. So I can have a self loop of 1 here, no problem. I can have a self loop of 0 here, no problem. And after that I can have a self loop of 0, 1. I don't have any problem. This is the explanation. Already I explained you. Now DFA for a string ending with A. This is an important thing that what we are going to do. I am going to construct a DFA that is going to accept set of all strings that are going to ending with A over the alphabet is sigma is equal to A, comma B. There are 2 letters in the alphabet. Okay. Now we are going to construct such a DFA machine. Now let me construct it. Okay. So ending with A, what is the minimum string? C is an infinite language or a finite language, means how many strings I can form over the alphabets A, comma B. In that I need to have strings that are ending with A. I can have A as a minimum string that is ever possible. Why? Because a string A means it is ending with A only. Okay. Can I have a string like BA? Okay. I can have a string with BAA. I can have a string with BBA. I can have a string with triple BAA. Like that I can, how many strings I can form? I can form infinite strings. So I can say that it is an infinite language. Okay. But remember one thing, whenever you are asked to design a DFA machine for a language which is infinite, you are going to always think about the minimum string that can be accepted by the DFA. When the language is infinite, you should always think about how to construct a DFA machine, minimum DFA machine for a minimum string. Then you are going to expand it. Okay, this is how we are going to do it. Now see it. I am going to construct a DFA machine for the language which is going to contain set of strings that are ending with A. So what is the minimum string that can be accepted by the DFA machine? It is A, simply A. So how many symbols are there? 1 symbols are there. 1 symbol is there. How many strings, how many states I may require? If there are n symbols, I may require n plus 1 state, isn't it? If there are n symbols, I may require n plus 1 states. So since 1 symbol is there, I may require at least 2 states. I am starting with Q0 is the starting state. And Q1 is the final state. So what is the minimum string that I can apply A? Means what? Q0 on A, it is going to Q1. That is the meaning of it. Q0 on A, it is going to Q1. Is this a DFA? No. Why? In order to say that it's a DFA, I need to apply all the states should consume all the input symbols. Q0 should consume A and as well as B, but it is not consuming B right now. And similarly, Q1 has to consume both the symbols A and B, but Q1 is not consuming A and B. So I need to make it as all the states should consume all the input symbols. And the second one is on applying a single input symbol on a state, you should go to only one and only one state. Okay. So that is the 2 rules that we need to remember. Suppose that if I apply B as a self loop on Q0, do I have any problem? I don't think that I am having any problem. What do you mean by that? Is a self loop means what? B, you can iterate B 0 or more number of times. You can either apply B or any number of times, or you won't apply B. Suppose that if I won't apply B, still I can reach the final state Q1 just by A, which is ending with A. Fine. Now suppose what happens if I iterate B on Q0 for 2 times, and finally I am going to arrive at the Q1 by applying A. So this is a string where it is ending with A only. So I don't have any problem on applying B as a self loop on Q0. Now is it a DFA? Is it a DFA machine? No, it's not a DFA. Why? I need to show paths for A and B on Q1 also. If I apply a self loop of A on Q1, do you have any problem? I don't think so. Why? See, suppose that Q0 on A, I am going to Q1. If I apply one more A, it is still ending with A only. Okay. Even if I won't apply A, still already I got one A. It's ending with A. So this is how we are going to analyze the things. Now we are going to see about the B, application of B. What happens if I apply B as a self loop on Q1? What happens? See, that the problem here is Once is Q naught on A, I am reached the final state. I have reached the final state. See what you mean by this self loop of A comma B means you can apply A comma B for 0 or more number of times. Assume a situation where I have applied B on Q1, okay, I remain in the final state only Q1. This is the string that is actually not ending with A. Why? Because of the B, right? So whatever the connection that what we have given is wrong. I should not apply B as a self loop on Q1. Why? With 1 A I can come to Q1. What happens if I apply one more B on Q1? Then it becomes AB. But this is a string which is not ending with A. So I can't apply self loop of B on Q1. Now this is wrong. So what is the right then? What is the right way to do it? See, you have reached Q1, the final state Q1, only after seeing 1A. If I see a B, then you go to some state from where I can reach the same state Q1 with the same with an A. See, once you have reached Q1, if I apply any B, you go to some other state from where you can come up to the final state Q1 with only A, right? So what is the state I can apply here? Q0, and this is an indication that is saying that you have applied a self loop of B on Q0. So you just iterate it. Now let me check it whether it is correct or not. Q0, suppose A I have applied, I have reached the final state Q1 and I have applied a self loop of A here, and if I apply B here, see AAB, is it ending with A? No, it is not ending with A. So it should be in the non-final state. Here Q0 is the non-final state. It is not final state, it is starting state. So AAB is not accepted by this machine. Fine. So if I apply one more A, I can come back to the final state. This can be accepted. Why? Because AABA means it is ending with A. This is how we are going to construct a DFA mission. Now, non-deterministic finite automata. Mathematically, you can represent the non-deterministic finite automata again with a 5-tuple notation only. And in that 5-tuple notation, as usual, you are going to have Q, you are going to have sigma, you are going to have delta, you are not going to have Q naught, you are going to have cap left. In a DFA mission that is imposing two rules. One is all the states should consume all the input symbols, and on the application of a single input symbol on a single state, you should not go to more than one state. You should always go to only one state. These two rules are violated here. You are given up. Okay. So such type of automata we say that it is an NFA, non-deterministic finite automata. What is your next move? I can't and I don't know. See, suppose what do you mean by that? Let me explain it. Suppose that Q naught, if I apply an input symbol A, I will go to Q1. On the application of the same input symbol A, I may go to some other state Q2. So this is how the NFA is going to behave. So can you, damn sure can you say that if I apply A on Q naught, you are going to only a particular state? No. Why? You are having several choices. Not only this, you can apply the same symbol A, you can go to some other state Q3. You can apply the same input symbol A and you can go to some other state Qn, like this. Okay, what is your next move? I don't understand, I don't know. That is why we say that it is a non-determinism. Such type of automata is called as an NFA. Okay. Now Q, sigma, these are the symbols Q, sigma and delta, Q naught, cap left. This is how we are going to have NFA for a string containing 0, 1. So already we have told you how to design a DFA mission to as a set of all strings that are containing 0, 1 as a substring. Now we are going to explain you how we are going to construct an NFA mission that is going to as a set of all strings that are containing 0, 1 as a substring. Okay, now let me explain it. See what do you mean by this 0, 1 that consisting of two symbols. We require at least 3 states, starting with Q naught, starting state Q1, and Q2 is the final state. Q2 is the final state. Okay. Now how I am going to represent it? 0 with 0 and 1 I will be reaching the final state. Okay. So once whatever that happens before this one 0, 1 as a substring, whatever that happens before that I don't care. and whatever that happens after getting 0 1, I don't care. This is how I am going to represent the NF emission. So I am going to construct an NF emission for the string that is ending with A. Now okay, already I have constructed a DF emission for a string that is actually ending with A, DF emission. For the same problem, we are going to construct a NF emission that is going to have a set of all strings that are ending with A. Now how we are going to construct it? Now as usual, the minimum string that can be accepted by the NF emission or DF emission is A. We require at least two states, A, and this is the final state. Okay, see, that is ending with A. Okay, before that whatever happens I don't care. Okay, I need to reach the final state with at least one A. That's it, that is my criteria. So whatever that happens before this, I don't care. Okay, so since I have reached Q1 with A, my condition is satisfied. That is, I am going to able to construct an NF emission that is going to accept set of all strings that are ending with A. So this is the way A with one A, that is enough for me to reach the final state. Whatever that happens before, I don't care. That's why I have applied A comma B as a self loop on Q0. Since I already reached Q1 with at least one A, means with at least one A means what? This is the final symbol, ending symbol. I don't care, even there is no need for me to apply A comma B on Q1. Why? Because I already got a string which is ending with A. Then whatever that happens, I just ignore it. But whereas in DFA you need to show path even for A on B, A and B on Q1. But in this case of NFA there is no such restriction. So you can be having a question in your mind that sir, suppose that if I have applied A on Q0, so the symbol A on Q0, I will be having two options. Either I may remain in the same state Q0 or I may go to some other state Q1. See, we always represent this one as a delta, that is a transition function. Q0 on A, we may go to Q0, or with application of the same symbol Q0 on A, I may be going to Q1. So there are two possibilities are there. That is, I am applying delta of Q0 comma A, I may go to Q0 comma Q1. So if I apply A on Q0, I may remain in the same state Q0. But you may be thinking that since the string is ending with A, you should be in the final state. Yeah, right. Yes, of course, small a is accepted, but you need to show at least one path where I can reach the final state. In this path, I may not be able to reach the final state Q1 by applying A, even though it is a value string. Understand that? Okay, but I am having one more path with the application of same input symbol A. I can go and reach the final state. So you show me one path from where we can from where I can reach the final state. If you are able to show it, it's DFA. Okay, so this is a fundamental difference between the DFA and NFA. In DFA, I need to show paths, means all the states should consume all the input symbols. That is the rule of DFA, thumb rule. But here you can clearly observe that I have not applied A and B on Q1, so there is no need. One rule is violated. What is the second rule? On the application of the same input symbol, I may go to only one and only only one state in case of DFA. But in case of NFA, on the application of the same input symbol on one state, I may go to two or more states. Here Q0 and A, I am going to Q0 and as well as Q1. That is the difference. I think you understood. So this is about the thing. For the same problem, we are going to introduce the NFA to DFA conversion. So let me explain you the NFA to DFA conversion. So NFA to DFA. What is the NFA? Okay, what is the NFA? For the language that containing set of all strings that are ending with A. How we have constructed? What is the minimum string that is A? This is the starting and A. Okay, I reach it to the final state. So whatever that happens at front at the beginning, I don't care. Once I reach the with this A as my end symbol, that's it, I have done. So this is about the NFA. So the same thing that what we are going to, this is what is called as a transition diagram. This is what is called as a transition diagram. So I will convert this transition diagram into a transition table. Actually, we are going to have a concept called as a transition system. We are going to have a concept called as a transition system, where we are going to have three notations for the same transition system. Either with the help of a transition diagram, I can represent the transition system, or with the help of a transition table, we are going to represent the transition system, or with the help of a transition function, means what, delta, we are going to represent the transition system. So there are three ways in which we are going to represent the transition system. One is transition diagram, this is the transition diagram, and transition table, and the transition function. Yes. Now this is a transition diagram for NFA that contains that they are going to have a set of all strings that are ending with A. So transition table, how I am going to draw a transition table for it. I am going to draw a transition table for it. See, I am going to have always rows as my states. In the row wise I am going to take, and in the column wise I am going to take input symbols that I am going to apply on states inputs. How many states are there in the diagram? 2. What are they? Q0. Second one is Q1. So remember one thing, Q0 is the starting state. Whenever I am going to represent it in the transition table, I am going to represent it with an arrow mark. Why? Because it represents the starting state. Whenever I am going to represent the final state in the form of a transition table, I am going to represent with a circle. No, that is how. So what are the symbols or their input symbols that I want to apply on the states A and B? So Q0 on A is actually going to Q0 and as well as Q1. So I can say that it is Q0 comma Q1. Q0 on B, there is no such transition. I say that it is fine. Q1 on A, no transition, fine. Q1 on B, no transition. This is a NFA table. Now I want to convert this NFA table into the DFA table, the equivalent mission. Remember one thing, we can convert each and every NFA into equivalent DFA. There is a certain procedure, I am going to explain it. So I am going to construct a DFA table. From NFA transition diagram, I have constructed NFA transition table. From this NFA transition table, I am going to draw the DFA transition table. So same thing, states, inputs. So what are the inputs here? A and B. What are the inputs here? A and B. Now understand this. In order to construct a DFA table, the first step that what we have to remember is, whatever the starting state of NFA is there, that is again the same as the starting state of DFA, and whatever the transition that you are seeing at the first row, you are going to dump them as it is. Starting state of NFA equal to a starting state of DFA, and dump whatever the transitions as a first row that what you are having in NFA as a first row in DFA. What is the starting state of NFA? Q0. You are going to represent this Q0 within the square braces. This is a standard notation. What is the first transition? Q0 comma Q1. What is the second one? It's a 5. Now you have already seen Q0. Okay. Whenever you are going to have a new entry, you have to take the new entry and you are going to progress. Let me explain you further. Here Q0 comma Q1 is the new state, right? You are going to get that new state of Q0 comma Q1 as a next row. Q0 comma Q1 as a next row. Now you are going to apply A on Q0 comma Q1. How you are going to apply A on Q0 comma Q1 means, I can say that delta of Q0 comma Q1 comma A. How I am going to explain you means, this is what is called as an extended transition function. I am going to write delta of Q0 comma A union delta of Q1 comma A. What is delta of Q0 comma A? That is Q0 comma Q1 union. Q1 comma A is 5. 5 is the empty set. So I'm going to have q0 comma q1 as a result. So delta of q0 comma q1 comma a is nothing but q0 comma q1 comma a is nothing but union of these two things, q1 naught comma q1. What is delta of q0 comma q1 on b? q0 comma q1 on b, it's a 5. So now you are going to check again these two entries. Have you visited q0 comma q1? You just look at the row. Yes. So you check it out. Already I have seen this one. Have you seen 5? No, I need to see 5. 5, that is 5 itself, nothing. So I have seen. Do you get any new states that are generated now? No. I have seen q0, I have seen q0 comma q0, q0 comma q1, I have seen 5. That's it. That is the end of it. Now the final step in DFA, in converting NFA to DFA, you have to identify the final states. What is the final state in NFA? It is q1. So wherever you see q1, you make the entire state as a final state. Where you can see the q1 here the q1 is there. So you can make it as a final state by just circling it. Okay. So this is the equivalent DFA mission. First, what we have seen, NFA transition diagram, NFA transition table, DFA transition table. Now it's the time for us to draw the DFA transition diagram. So how many states are there here? 3 states. You can say that 5 is a dummy state, just you can eliminate it. Okay. So q0 is the starting state, q0 comma q1 is the final state. Now you apply it. q0 on A, it is going to q0 comma q1. q0 on B, it is not going anywhere. q0 on B is an empty. Okay. And q0 comma q1 on A is going to have a self loop. Okay. And q0 comma q1 on B, it is going to a dummy state. It means what is a 5. We can say that it is a 5. Next 5 we are going to apply it. So this is a set of all strings that are ending with actually A. We are going to have the DFA mission that is going to have set of all strings that are ending with A. Okay, this is how we are going to check it out. q0 on A and q0 on B. Now this is an NFA mission. We have seen it. q0 on A, it is going to q0. q0 on same A, it is going to q1. And we are going to have q0 on B. q0 on B, here I have missed out. q0 on B, it is actually going to q1. Let me draw it. Let me make you better understand the things. Yeah. q0 on A, it is going to q0 and as well as q1. q0 on B, it is going to actually q0. It is not 5, it is actually q0. Okay, let me just, yeah, you can understand it in a better way. Okay, yeah. So q0 on B, it is actually going to q0. And q1 on A, not going to anywhere. q1 on B is also not going anywhere. Now I need to convert this NFA table into DFA table. So how I am going to construct a DFA transition table? States, inputs. Okay, what are the states and what are the inputs? So states are q0, starting state of NFA equal to starting state of DFA q0. Okay, input symbols are A, B. q0, first transitions you need to dump it out. q0 comma q1 comma q0. This is the first one. Have you seen q0? Yes, check it out. q0 comma q1, it's a new state, take it out. q0 comma q1. q0 comma q1 on A, it is going to q0 comma q1. Have you seen q0 comma q1? Yes, check it out. q0 comma q1 on B. What is the union of this? It is q0. q0 comma q1 on B. This is q0 comma q1 on B, q0. Have you seen q0? Yes. So there is no state that is newly generated. Now you are going to halt it. What is the third step? You need to identify the final states. So what is the final state in NFA? It's q1, right? This is q1. Now wherever you see Q1, you are going to make it as final state. Now you draw the DFA table, DFA diagram. Q0 is the starting state. You are going to have Q0 as the starting state, and Q0 comma Q1 is the final state. So Q0 on A is going to Q0 comma Q1, and Q0 on B is a self loop. Q1 comma Q1 on A is a self loop. Q0 comma Q1 on B going back to Q0. So this is nothing but a DFA diagram that what we have constructed. So this is how we are going to construct an equivalent. We can convert in each and every NFA mission into the equivalent DFA mission. Now we are going to have a concept called as NFA with epsilon transition to NFA to DFA. So we are going to see it. So for that, what we are going to see is we are going to make use of the same concept, that is NFA mission, that is going to always as a set of all strings that are ending with A. Okay, we are going to just use the same example. Now let me explain you. How I constructed this NFA with NFA mission for the set of all strings that are ending with A. Q0 with 1A I can reach to the final state. Whatever that happens before, I don't care. So this is NFA mission, and I'm adding one more state. Say that with epsilon I am going to some other state that is called as another final state. Let me assume that it is a final state. So it is we say that it is an NFA mission with epsilon transition. Why? Because you are seeing epsilon symbols on the mission. Okay, now I need to convert this NFA with epsilon transition to NFA mission. How I am going to convert NFA mission with epsilon transition to NFA means we are going to use certain formulas. The first formula that what we are going to use is delta dash of Q comma A is equal to epsilon closure of delta cap of Q comma epsilon comma A. This is the formula that what we are going to use. And the second formula we are going to use is delta cap of Q comma epsilon is equal to epsilon closure of A. Epsilon closure of A. Delta cap of Q comma epsilon is epsilon closure of Q. Sorry, it is Q. Epsilon closure of Q. Okay. So what do you mean by epsilon closure? Let me explain you. Okay. First I am going to explain about calculate the values of delta dash of Q comma A. What is the alphabet here? The alphabet consisting of two letters. What are they? A comma B. So understand this. Sigma consisting of two letters A comma B. Now since the alphabet is consisting of A comma B, I need to apply A comma B on Q0, Q1 and as well as Q2. So I need to calculate Q0 on A, Q0 on B, Q1 on A, Q1 on B, Q2 on A, Q2 on B. So delta dash functions. This is the first delta dash function that what we are going to see is delta dash of Q0 comma, okay, what is the first symbol? A. How I am going to explain it? Delta dash of Q0 comma A means epsilon closure of, okay, delta cap of Q0 comma epsilon comma A. How I am going to explain it? Delta cap of Q0 comma epsilon means epsilon closure of Q0. Here Q means Q0. Epsilon closure of Q0 means you always include Q0. From Q0 by applying epsilon, to which state you can reach? Actually, on applying epsilon on Q0, I can reach no state. By there is no such transition that is called as epsilon on Q0. So I am going to have epsilon closure of Q0 comma epsilon means delta cap of Q0 comma epsilon means epsilon closure of Q0. Epsilon closure of Q0 is nothing but Q0 only, right? From Q0 with epsilon, I am not going to any way state. Anyhow, I am going to include the same state Q0 on which you are going to apply the delta cap. So what is this value? This value will become Q0. Okay. So that means epsilon closure of delta of Q0 comma A. q naught comma a. So what I can find, q naught comma epsilon closure of delta of q naught comma a means I can have q naught and as well as q1. Epsilon closure of q naught comma q1. So epsilon closure of q naught comma q1 is epsilon closure of q naught union epsilon closure of q1. So epsilon closure of q naught union epsilon closure of q1. So that is the value. What is the epsilon closure of q naught? It's a q naught only union. What is the epsilon closure of q1? Q1, from q1 I can reach to q2. So I can say that it is q1 union q2. So q naught comma q1 comma q2. So delta dash of q naught comma a is epsilon closure of delta cap of q naught comma epsilon comma a. What is the value of delta cap of q naught comma epsilon? Means epsilon closure of q naught. What is the epsilon closure of q naught? Q naught only. Okay. So delta of q naught comma a, delta of q naught comma a means I can reach to q naught and as well as q1 also I can reach. So epsilon closure of q naught comma q1, that is now q naught comma q1 comma q2. So this is the value of delta dash of q naught comma a. Similarly, I need to calculate the delta dash of q naught comma b. So epsilon closure of, this is epsilon closure of delta cap of q naught comma epsilon. So epsilon closure of q naught, epsilon closure of q naught means q naught only and b. So epsilon closure of delta of q naught comma b. What is the value of q naught comma b? That is q naught only. So I can have q naught. I can have q naught. Right. That is the values of delta dash of q naught comma b. And I am having the third one, transition function 1, delta dash of q1 comma a. Delta dash of q1 comma a. So that is the value that I am going to have. So what is the value of delta dash of q1 comma a? Means epsilon closure of delta cap of q1 comma a means epsilon closure of q1 means q1 comma q2 comma a. In this way we are going to follow the things. Okay, this is about NFA with epsilon transitions to NFA without epsilon transitions. Later we can convert it into the DFA. Later then we can convert it into DFA. So this is the minimization of automata, that what we are going to see in the next topic. We are going to see in the next topic. Now you just remember it. There are mainly two important formulas in converting the NFA machine with epsilon transitions to an NFA machine without epsilon transition as well as to DFA. So what is the first formula I have written? The first formula is delta dash of q comma a is equal to epsilon closure of delta cap of q comma epsilon comma a. The second formula that what we have written is delta cap of q comma epsilon is equal to epsilon closure of q. This is how we are going to solve the problems. Okay, so we are going to see in the next class how we are going to minimize a given DFA machine and as well as a working example of NFA with epsilon transition to NFA, and then we are going to convert it into DFA. Thank you.